Afternoon session. My name is Robert Kerr. I'm from the University of Warwick. Our first speaker is a legend in the theory of turbulent convection instabilities and bounds, Fritz Busse. And the theme, by and large, of this afternoon section looks like it's largely things to do with dynamos and MHD. First talk by Fritz Busse, unusual properties of turbulent convection in dynamos and spherical shells. And you have 28 minutes, and then I will ask for some questions.
Thank you. We make a transition now from the shallow systems to the more deeper systems, and the kind of systems we have in mind here is the Earth's core, or maybe the cores of other planets, and we are interested in the kind of convection which is going on there and its turbulent properties. And of course, connected with this is then the question of the magnetic field generation, because all the planetary interiors with strong convection usually exhibit also magnetic fields. And I will start with just the non-magnetic case, so we don't get into MHD yet, where we deal with convection in a rotating system, and we have the usual equations in the Busse-Naess approximation. The attempt here is to do the physics as simple as possible, so that all important aspects are there, but we don't attempt to be very realistic. Since the flow is in good approximation incompressible, we can use this general representation in terms of poloidal and toroidal components of the velocity field, and we will use the same thing later on for the magnetic field. I don't want to bother you with the equations here. They are solved numerically, and the only thing you should perhaps remember is the Rayleigh number based on this thickness of this rotating shell, and the Coriolis number, which is just the dimensionless measure of the rotation rate, and the Prandtl number, which is the ratio of kinematic viscosity to thermal diffusivity. Now this system of equation allows actually in fairly good approximation analytical solution, which is compared here with the thick lines, which are numerical solutions, and you see that the critical Rayleigh number goes up as expected very strongly with rotation rates, and it depends also on the Prandtl number. Down here, where the analytical expression is no longer good, you have convection in terms of inertial oscillations. The convection for Prandtl numbers of the order 1 assumes this form of those columnar rolls which travel around. That's why they feel the Rossby wave dynamics, so they have to travel, and they are elongated because of the Proudman-Taylor theorem, which tries to minimize the z dependence, the z along the axis of rotation coordinate. Here just for comparison, inertial mode convection is quite different and is usually attached to the equatorial part.
Is what was tau? What is
Oh, that's tau squared. Excuse me. I have a different notation here. This convection columns, as you increase the amplitude, they go through various type of instabilities. For instance, this amplitude vacillations, where the amplitude is sometimes getting rather low and then increasing again. And associated with this nonlinear properties of convection is a strong differential rotation. The differential rotation is shown here with amplitude of the average phi and red lines indicate positive, that means prograde motion, blue lines is retrograde. And here's just the radial component shown in the mid-surface of this shell, but that's not so relevant at the moment. There is some difference between convection at high Prandtl number and low Prandtl number. At high Prandtl number, like p equals 15, the convection has a differential rotation which no longer is geostrophic, but is more a thermal wind type rotation, because the convective heat transport depends strongly on latitude, while at low Prandtl number, say Prandtl number equals 1, we have this strong geostrophic differential rotation which does not depend on the coordinate in the direction of the axis. I also like to emphasize here that at low Prandtl number, the vortex has looked down in the equatorial plane, spirals strongly, and the Reynolds stresses associated with this kind of motion are very strong and are responsible for generating a strong differential rotation, while at high Prandtl number this does not happen very much this way. Now, as Rayleigh number is increased, we go from this bucculating state where you see the amplitude of the fluctuating components of the motion, and you see also the differential rotation indicated by the red line. We go to higher and higher Rayleigh number, and the periodic motions then become aperiodic and chaotic, and because the differential rotation is generated by the Reynolds stresses, it grows much faster. It goes proportional to the square of the amplitude of convection. It tends to exceed the convection amplitude by far, and in the end we come to a state which exhibits in a turbulent way some regularity. But before we get there, we have to talk about localized convection, and this is a phenomenon that the differential rotation has a precarious balance with the convection, because it's generated by convection, but on the other hand the differential rotation disrupts convection. It shears off the convection columns, and it has a result that convection ceases to exist over most of the spherical shell, and only at the localized place we still have this convection. And of course this convection is needed to sustain the differential rotation, and in a sense there is some recuperance of the buoyancy as the differential rotation goes around here. It regenerates the original buoyancy profile, and that of course then is feed into this convection region and gives sort of a feedback for the convection there. So you see this in the temperature as well as in the streamlines, in the equatorial cross-section of the streamlines, and it's this precarious balance which at higher Rayleigh number turns into a even more unusual type of balance, which is shown here, namely that the differential rotation, which is now very strong, cuts off convection completely for most of the time, and once the differential rotation is no longer sustained by Reynolds stresses, it must decay, of course, on a viscous time scale, and if it has decayed enough, then convection can start over again and increase, but at the same time it generates the differential rotation and sort of digs its own grave, and it ceases to exist, and differential rotation has to decrease again until convection can go up again. And this is all in a turbulent regime, but surprisingly regular. the time scale, of course, is governed by the viscous decay time. We see this irregularity of convection due to turbulence is a Nusselt number plotted here, and but we can see it.
These are functions of time.
Yeah, the time is, oh yeah, it's too small here. It's function of time.
And is that the total energy, and then it's split into colloidal and toroidal? Oh, that doesn't make sense.
Yeah, it's a fluctuating. That's the convection part of toroidal and colloidal energy, while the mean energy is essentially only toroidal. There's no mean colloidal energy. Now, this kind of relaxation oscillation we can see here when we look at the equatorial plane again. Here's our differential rotation, and now as time goes on, it decreases, and it becomes rather weak here, and as it's weak enough, now convection starts over, and but as soon as it comes in, its Reynolds stresses generate a strong differential rotation, as you see here, and associated with this of now is the disruption of convection. It's decaying, and here we have essentially a state of no convection, and you have to start all over again. I mean, there are, of course, various combinations of relaxation oscillations and localized convection, as you might see here, where convection is localized, but then the differential rotation is generated by this localized convection and cuts off the convection until the differential rotation decays enough and convection can come in again, and there are periods of this type. Now, when you have a dynamo, and I sort of go ahead of my talk here, then it sometimes happens that the dynamo is just barely making it, and in this particular case it decays, it tries to come up again but failed, and the magnetic energy shown in black here goes to zero. And what happens there is that the convection, which was sort of characterized by fairly low differential rotation, then takes advantage of the decaying magnetic field, and the differential rotation grows, and as the magnetic field has disappeared, it's those relaxation oscillations which come in again. Now that indicates that the magnetic field acts as a brake on the differential rotation, and because the differential rotation is relatively weak here, convection can be fairly strong, and we see this in the Nusselt number. Here the Nusselt number in the dynamo case is quite high, but when we go back to the case without magnetic field, we have only those peaks in the Nusselt number. On the average, we have less than a few percent of the heat transport which we had in the magnetic case. And this, I think, in a nutshell, is all what planetary dynamos and actually perhaps some stellar dynamos as well are all about. The magnetic field helps them to get an efficient heat transport in a rapidly rotating case. But now let's go to the dynamo case. We have the same equation as before. There's one more parameter here, and that is the magnetic Prandtl number, where the magnetic diffusivity is in the denominator, and this magnetic Prandtl number appears here in the induction equation for the magnetic field. So there's just one more equation we have to deal with, and that's one more parameter. The magnetic field is represented similar in poloidal and toroidal part. The toroidal part is the one which we can't see from the outside because it has to vanish at the core surface. And yeah, I mean, there's one could speak a lot about various types of dynamos, but principally it's just a bifurcation like any other hydrodynamic instabilities. We have here instability involving the magnetic field. We have a new degree of freedom, and when we start off with convection coming from a spherical symmetric state, getting those m-periodic drifting Rossby waves, then we have possibilities of new bifurcations involving the magnetic field in addition to those which do not involve a magnetic field, which we have already discussed. And this is not what I want to talk about. I just want to mention that dynamos exist whenever you have strong enough convection given by the Rayleigh number here, and for very low magnetic Prandtl numbers you have difficulties finding dynamos. There's a regime here given by those two bounding lines where dynamos are possible, and it indicates that too high Rayleigh numbers are not good for dynamo action either, because they tend to expel the magnetic field, the eddies expel the magnetic field, and that makes them less efficient as dynamos. Among the dynamos, there has been known for quite a while that there are actually two basic types. One which is characterized by a very high mean magnetic field that is usually at higher Prandtl numbers, where the fluctuating part of the poloidal field is less than 1 or only a little above 1. And then there are other dynamos at low Prandtl number which have a strong fluctuating magnetic field and only a relatively weak mean magnetic field. And this suggests that there is actually really a hysteretic system here. But before I show that, I want to characterize these two types of dynamos. This is the one with a strong mean magnetic field indicated in black here, which is associated with a not too strong mean azimuthal field given by the red color here. The fluctuating dynamo has a rather weak mean magnetic field and strong fluctuating components. The corresponding kinetic energies are shown here, and we see that the differential rotation is almost cut to 0 by the mean magnetic field here, which is so strong, while in this case there is still some sizable differential rotation, and the convection amplitude is also the same. If we take out the magnetic field, then in both cases we get the same kind of relaxation oscillation which we had before. I should have emphasized here that both these dynamos occur now for the same parameter values, and there is a quite extensive area of this parameter values where we have two different turbulent states. For instance, if we just fix the magnetic Prandtl number here, then as a function of the Prandtl number we have the two different dynamos which differ in the ratio between fluctuating and mean poloidal magnetic energy by about a factor 10. And we can see that this is also visible if we fix the Prandtl number and just change this ratio, or if we fix both Prandtl numbers and just change the Rayleigh number, we still have this distinction. What's surprising or typical is that the Nusselt number of convection is the same for these two types of dynamos. So they are both equally efficient in helping the heat transport. The heat transport is higher than the one without magnetic field, which is indicated by the green point here. So they do their job, but in a very different way. And yeah, perhaps I show here another picture of the two dynamos. The one with a strong magnetic field, strong dipole, is indicated here, and it has rather weak differential rotation. There's no it's just sort of a left thermal wind relationship, while in the fluctuating dynamos we see the fluctuating component are actually quite strong here, and I should have pointed here for the differential rotation. This is the differential rotation of the thermal wind type, and here we have still a weak geostrophic type differential rotation. So we have two different states at the turbulent states at the same parameter range, and this goes over quite a quite a wide range, and is seems to be rather typical. Besides the dipolar dynamos, of course, there are also quadrupolar dynamos, which are always oscillating. We see the oscillation exists in new flux tubes generated in the equatorial plane, and then expanding and shifting the old flux towards higher latitudes, and where they are then decaying, and so you get a period of this flux oscillation in this form, and the poloidal field then looks like this. Here we also can have two different states, as indicated here. We have a dynamo which is a mixed dynamo with a quadrupolar field and the dipolar field, and another dynamo where the quadrupolar field looks very much the same as in this mixed case, and the dipolar field is just decaying forever. It goes just down. So there are various states of dynamos, and if I have just a little time, then I want to show something about the reversals of the Earth's magnetic field, which is actually generally regarded as a typical chaotic feature of dynamos in the Earth's core, but may not be so. And the reason is that the dynamo in the Earth's core may be actually also oscillatory. Here we show an oscillatory dipolar dynamo, again flux generation in the equatorial plane, pushing it up to a higher latitude. And let's look at the poloidal field, which then reverses here, and after the cycle comes back essentially to the origin, to the old part. And now this is not so typical, because often it is if you get a field which is just where just the toroidal flux is oscillating, and the poloidal field takes only little part in this oscillation, it just changes its amplitude. Here, starting off with this case of strong dipole, it gets very weak and stays weak for a little while, and then after the toroidal field has reversed, it comes up with the same polarity. This can happen in this particular case. It happens too. We see the oscillations in the toroidal field. The poloidal field just gets weak. There's a tendency of replacing the polarity of the poloidal field, but it doesn't work out. This opposite eddy here doesn't win. The old field recovers, and it's just got weak, and we are back to the old polarity. Now, this may happen in the most cases, but there are some cases when it does not happen, when this new flux trying to replace the old flux actually wins over and replaces the old flux. And in this case, we have indeed gotten a reversal, and this is, seems to be what might happen in the Earth case as well. Let me first show here the typical oscillations, which, since we are just plotting the dipole component here, they oscillate only in amplitude, but once in a while there is a reversal taking place. And this is another case where many oscillations take place and then reversal comes up in an irregular fashion. And this seems to be what is also observed in the paleomagnetic record. Here we see just for the past million years the amplitude of the magnetic field, and there was a reversal at one time, but the amplitude of the magnetic field went down many other times, and these are called global excursions, and this I would interpret as a typical oscillation, while once in a while this oscillation gives rise to reversal. So it is not the typical chaotic response of the system, but just something which happens on top of the regular reversals.
Where is 0 on these plots?
0 is essentially down this line here. That's the zero
That's the
energy.
magnitude of the, not the direction of the magnetic.
Yeah, it's just the magnitude. And I mean, these reversals, I should also say, they have the time scale of the magnetic time scale of the Earth's core. They have been, I mean, this is about 30,000 years or 40,000 years, and they have just recently been discovered, or more of them have been recently discovered, and it could be that this time scale gets more regular as better data coming along. Thank you for your attention.
Keith.
It appears that the length scale of the fluctuating part of the magnetic field and the velocity field decreases as the Reynolds number or the Rayleigh number increases, and therefore a mean field description might help us to understand what's going on. Would you think that your dynamos are of the alpha omega type?
Yeah, with some restrictions. First of all, the alpha is highly anisotropic, and secondly, we find that the omega effect, which is still there in both cases of both dynamos I'm talking about, is supplemented by some generation due to high harmonics. I mean, there's so it's not the only process, but there's things which are not covered by the usual mean field approach.
But it would be a starting point.
Yeah, it would be interesting whether you find this bistability with the mean field approach as well. I am not sure about that.
Perhaps I missed it. Could you comment on the role of the magnetic inertia of the conducting inner core on these reversals? I mean, one imagines if the field's locked into the inner core, then it's difficult to diffuse out and might stabilize the reversal.
Yeah, this effect, of course, is known from the work of Hollerbach and Jones, and but in our simulations we don't find it actually, and we agree with Johannes Wicht, who has investigated this effect even earlier than we did, and he also claimed that he can't find this effect. The field is too fluctuating to really penetrate deep into the inner core, and the inner core is just too small to have this kind of effect.
Other questions?
Can you go back to you had this intriguing diagram of the magnetic Prandtl number and the Rayleigh number.
Yeah. Yeah. You mean this one?
No, you sort of had two lines coming together and had the magnetic Prandtl number on the x-axis. Yeah, the regime diagram.
Three-dimensional thing.
Oh, yeah. That
So
was
I
really
just trying to.
yeah.
Well, what was the lowest magnetic Prandtl number that you find a dynamo?
So, I mean, the lowest magnetic Prandtl number was about 0.1 in this case. But of course, if we could go to higher rotation rates, I mean, this was done for, should say somewhere, for tau equals 10 to the 5. And if we could go to higher taus, then we might go to lower magnetic Prandtl numbers and still find dynamos.
You want to get to 10 to the minus 6 on the also.
Yeah, if we can go to tau equals 10 to the 15.
Okay, so you think you can reach, if you had a big enough computer?
Yeah. Actually, Christensen looked at this and he sort of derived the power law for this, and it seemed to work that way.
Okay. Anyone else have questions? We can discuss it at a break.